Hello everyone, my presentation paper's title is Adversarial Domain Adaptation for Speaker Verification using Partially Shared Network. I'm the first author, Zheng Yangchen. Although speaker verification system has achieved great improvement in the last few years, there are still challenges existing. For many cases, speaker labels are unavailable. The well-trained speaker verification system from one domain usually suffers a lot of performance degradation when applied to a new dataset from different domain. So it is very necessary to find an effective method to adapt a well-trained model of source domain data to a new domain without the speaker label provided. The common method to solve this problem is using adversarial training to match the embedding distribution of source and target domain. And I will introduce some related works using such method. In these two papers, the authors both use the adversarial training strategy to learn domain environment embedding, specifically using GAN-based laws to minimize the mismatch between source and target domain embedding distributions. The source and target domain data share the same embedding instructor. With such shared architecture, both papers show that the adversarial training cannot improve the performance of target domain as expected. In our experiment, we will detailedly explore why such method did not make difference. And in another work of ICASP 2019, the authors also used the adversarial training to extract the domain environment embedding. But the encoder of source and target domain data are independent. Results show that such architecture can obviously improve the performance. Here we have some inspiration. Intuitively, because of the distribution mismatch of different domain data, the embedding instructors for different domains should also be different. Besides, considering the tasks for the source and the target domain are the same, it should be better to share some layers of source domain instructor with the target domain embedding instructor. Here, we propose the partially shared network. Different from fully shared network, two parallel embedding instructors are designed for data from source and target domain. And different from independent embedding instructor for source and target domain, the parameters from source and target domain embedding instructor at the same layer can be either shared or not. The embedding instructor here it uses the TDN configuration as the X vector, and there are 5 TDN layers and 1 dense layer in it. And the best configuration of such partially shared network will be explored in our experiment. To train the new network, 3 losses are jointly optimized. The LC loss is the speaker classification loss for the source domain data. Here, we also use the adversarial training strategy to learn domain environment embedding, and the Weierstrass GAN loss is used here to achieve this goal. We denote this loss as LW. Besides, for the unshared layers, a regularization loss, LR, is used to constrain the weight of target domain embedding instructor not far away from source domain. This regularization loss can prevent our model only focusing minimizing domain mismatch and also keeps the speaker discrimination ability from source domain. Then I will introduce the dataset used in our experiment. The data from NIST SRE 2004 to the NIST SRE 2010 and the switchboard are used as the source domain data. All this data is in English, and the speaker labels are provided. The target domain data is from NIST SRE 2016, and the data language are Cantonese and Tagalog. No speak labels are provided for target domain data. In our first experiment, we jointly trained the source and the target domain embedding instructors. The speaker classification accuracy, vector distance, and the test equal error rate for different partially shared configuration are shown in the figure. For the partially shared configuration, 1 and 0 denotes sharing or not sharing the weights of a corresponding embedding instructor layer in order from input to output. From the figure, we find that the equal error rate is both influenced by the speaker accuracy and the vector distance. Higher speaker accuracy and the lower vector distance make the equal error rate better. To answer the question that why fully shared network, the all ones configuration in this figure did not make difference, we found that fully shared architecture cannot effectively reduce the vector distance and hurts the speaker discrimination ability at the same time. Besides, we also found the totally unshared network is not optimal. Since the main task of this paper is to compensate the domain mismatch, in our second experiment, we decided to keep the speaker discrimination ability by feeding the parameters of source domain embedding extractor. And the parameters of source and target domain extractor are initialized by a well-trained extractor from source domain. Here we found that more layers are unshared, the smaller vector distance is. But the smallest vector distance configuration doesn't correspond to the best result. Results show that sharing several input layers is best. A possible explanation is that the higher level information, such as language, is mainly abstracted in the higher layers. So it is helpful to keep different parameters at higher layers for the two extractors. Here, we compare the best configuration results of our partially shared network with the baseline and the fully shared network. The baseline system only trained the model on the source domain data and test on the target domain. The fully shared system using adversarial training strategy to minimize the embedding distribution mismatch from different domains. And the source and target domain data shared the same embedding structure. From the results, we found that the performance of our proposed partially shared network exceeds the baseline and FSN by a very large margin. Finally, we explore the impact of regularization laws, and the unshared network architecture is the best architecture in the last slide. From the results, we found that when the weight of the Weierstrass loss is big, which means we tried very hard to minimize the distribution mismatch, the existence of regularization loss is significant. And when the weight of Weierstrass loss is small, the regularization loss makes small improvement. Thus, the regularization loss is necessary and can make the result more stable. In conclusion, partially shared network is better than a fully shared network and unshared network. Sharing layers close to the input is better. Blindly minimizing the domain mismatch is not advisable. The speaker discrimination ability should also be kept at the same time. The regularization laws in our paper can achieve this goal. Thanks for listening.